Start by thanking the organizers for inviting me and for organizing this nice conference with a nice bouquet of talks. I'm talking about some story which is already to some extent has some history. Let me just give the motivation. So I work with a compact Riemann surface X. And G of X is the genus of X. I assume, well, for the beginning, it can be bigger or equal to 1. Later on, I will restrict to G of X bigger than 1. And then, I think everybody in this audience knows that in his fundamental paper in the mid-80s, Faltings introduced this new constant associated compact Riemann surfaces, which I call Faltings delta function of X, which, before I give a precise formula, can roughly be understood as the distance of X in the moduli space of curves of genus G, Gx, to its boundary in the Weil-Petersen metric, and then you take the log of this distance, and that's roughly, that measures roughly Faltings' constant, so to say. So originally, the formula was given defined in terms of the Riemann thetas, so to say. Or yes, something like this. And but rather complicated formulas, which at first sight are not so easy to handle. And then, Faltings himself treated the case G equals 1 for elliptic curves, where he related Faltings delta of X to minus log of the Petersen norm of the delta function. Well, tau is the period of the elliptic curves, something like this. And then for G, so this was Faltings in his paper already, and then G equals 2, Jean-Benoit with Mestre and Moret-Bailly. They related Faltings delta of X for curves of genus 2 to minus log of the chi10 of the period, so to say. Chi10 having been defined by Sagier in his talk, the product of the squares of the even thetas, the 10 even thetas. And I guess, there's also formulas for G equals 2, probably also the names I have written before. But I think also Robin, De Jong, there seems to be also formula. I haven't checked precisely the literature relating it to what I could call chi18, which is again the product of the even theta functions in genus 3. So the point is, what I have been originally jointly with J. Jurgensen interested in to getting the hands in the quite general case on this function, in particular also trying to get estimates of this function. But we basically have not been able to do this via the Riemann theta functions. And so we took a hyperbolic approach. And so I revisit in the first part, again, this hyperbolic approach. And then what has been, so to say, then once you have this representation in hyperbolic terms, which is somewhat ugly, so to say, but still you can do it. And then the next task was really to get on to estimate. So estimate a Faltings delta in terms of, well, the genus of X, which I now assume then bigger or equal to 2, the smallest eigenvalue for the hyperbolic Laplacian, smallest non-zero eigenvalue. I'll write things down more precisely in a minute, and what I call Lx, length of shortest closed geodesic. So that was then, so to say, the aim to really, from this complicated formula, which we will see, to really get down to these basic invariants on the underlying Riemann surface. And that's what in the past year we have done effectively, I think. And it was basically Parshin who motivated us to do this, because a long time ago he had his approach of estimating omega squared for estimating the height. And then he had the Archimedean contribution in terms of Faltings' delta function, and then he asked us, so to say, to pin down this contribution from the Archimedean contribution as explicit as possible. So, okay, so let me now be precise, so I come to the basic notations. Okay, so now X as above, compact Riemann surface, genus now bigger or equal to 2, and then I uniformize X by the upper half plane, so H mod gamma with gamma in PSL2R, subgroup, a function subgroup, co-compact and torsion free. And now I need, H, probably I should write down the upper half plane, Z and C. I usually write X plus IY real and imaginary part. And now I need the metrics, so I have the hyperbolic metric. I write down the corresponding 1-1 form locally. So mu index hype of Z, the corresponding 1-1 form is, well, I over 2 dz bar over the imaginary part, Z squared, or if you want dx dy over y squared. And then the hyperbolic metric, of course, then gives rise to the hyperbolic distance. This I denote like this, between points, and the hyperbolic volume, well, of X. And then also the Laplacian, which was in question already above, in local coordinates. I take it with a minus sign. And the spectrum I denote as indicated above. So the zeroth eigenvalue is lambda x0, and then lambda x1 is the smallest non-zero eigenvalue, etc. So that's all the hyperbolic data. Well, one thing I probably have to say that sometimes I scale the metric and I call it in scaled hyperbolic, so S-hype. So I divide just by the volume so that the total volume of the Riemann surface has volume 1. And then correspondingly one has also another metric, the canonical metric, so this metric of course comes from the covering space and has curvature -1. And then of course more algebraically you have the metric obtained as the pullback via the Torelli map from the Jacobian. And this I call the canonical metric, nu can of Z, the corresponding 1-1 form, which you obtain by I over 2, 1 over the genus, sum over an orthonormal basis of holomorphic 1 forms, basically. Omega j, which omega j bar, where omega j from 1 up to the genus is an orthonormal basis of the space of holomorphic 1 forms, gamma x, omega x, 1. And when you do the usual game in Arakelov theory, so you go to the associated Green's function, then you can associate to the canonical metric the residual canonical metric. Then we get well, here I write the metric. Then we get the Arakelov metric on omega x1, so to say. So that's the one which makes the residue map into an isometry, so to say. So these are the notations which are quite standard, I think. Now I have to a little bit more of an analysis, so I have to introduce the Green's function. I mean, I just introduced the notation. I don't give you the formulas because these are a little ugly. So hyperbolic Green's functions, hyperbolic heat kernel. So it's for, this is for functions, so to say. So, I mean, you know, there's a formula K for the universal covering. There's an explicit formula. It depends on time variable and Z and W. And in fact, it only depends on the hyperbolic distance between Z and W. And there's an explicit formula. And T is here a positive real number. And the Z and W, of course, in the upper half plane. And by averaging over the group gamma in question, the covering group, you get the hyperbolic heat kernel for the Riemann surface in question. So it's just the sum over all gamma and gamma, which is torsion-free and co-compact, KH, T, Z, comma, gamma W, gamma acting on W. So now, I mean, by some slight use of notation, identifying X with its universal cover. So here, Z and W are in X, so to say. Okay. And this, as a shorthand, we basically just need the sum, I mean, over the hyperbolic elements, so to say, and I call this HKX, and I only need it on the diagonal. This is the sum over all gamma and gamma, gamma different from the identity element, KH, T, Z, gamma Z. So that's the part from the heat kernel which I need, so to say. Okay, so. And then the next ingredient I use as a notation is Selberg zeta function, which was on the board, I think, already, for gamma. So let's just briefly recall it. So my notation, I take curly H of gamma to be the set of conjugacy classes, in gamma conjugacy classes, of primitive hyperbolic elements of gamma. And then the Selberg zeta function is a product over these primitive hyperbolic conjugacy classes with local factors. And the local factors are easily given. So let's just write it down. So we have Z, I call it Zx of S. So S is now complex parameter with large enough real part. The product over all gamma in curly H gamma. Local factors, Z gamma of X, and the Z gamma of X, the local factors are giving product n from 0 to infinity, 1 minus e to the s, where is it, n plus n, s plus n times L gamma. And L gamma here, L gamma is the length of closed geodesic associated to gamma. So gamma gives rise to a homotopic class, and so it has a unique geodesic in there, and the hyperbolic length of that is denoted by L gamma. This comes here as the weight, so to say. Okay, so one thing to be kept in mind. So Zx of S has analytic continuation to C, and it has a simple 0 at s equals 1, simple 0 at s equals 1. And so one quantity which is going to be of interest for us is the limit as s goes to 1 of the log derivative of the Selberg zeta at s equals 1, so to say the constant term of that log derivative at s equals 1. And now I'm almost through. I need a final ingredient, and that's just to recall the analog of the prime counting function. So it's a prime geodesic counting function. So the prime geodesic theorem. And I just need it because there is an implied constant which will be of importance later on. So prime geodesic theorem, last bit of notation. Okay, so I take eigenvalues which are small, so in the interval between 0 and a fourth. And then for this I defined as usual the corresponding S value, which is 1/2 plus 1/4 minus lambda xj, that's the usual notation. And with this xj, I have the prime, well, not yet, I first introduce the prime geodesic counting function. So it counts the number of gammas in my curly h of gamma of length e to the L gamma less than u, and here u is a real number bigger than 1. And using the integral logarithm, so we have the prime geodesic theorem. So pi x of u has the known Lie term like in the prime number theorem. So Li of u to the sxj, and a sum over the small eigenvalues, lambda xj less than a fourth, with these sxj's, plus a correction term Ox, which is u to the 3/4 times the logarithm of u to the minus 1/2. And the point is now, in this error term, there's an implied constant going along, and so we have this. Let me write this. This is even for this is for u bigger than 1 even here. And then so to say we call definition, so to say we call the infimum of implied constants in the Ox term, we call it C Huber of X, so to say. So this is thanks to Heinz Huber, who basically did this a long time ago, this prime geodesic theorem. And so this constant shows up here, and we take the infimum of all the possible constants showing up here, and we denote it like this. Okay, so that's all the ingredients which I need for now giving the next section. So now this is already section 3, I think, yes. Delta Faltings of x in hyperbolic terms. Okay, so here I start with a precise definition. This goes basically back to Soulé, and so to say arithmetic Riemann-Roch theorem for curves, which shows that you can give Faltings delta of x as a quantity which I define in a minute. So it's minus 6 times d index AR for Aracale of x plus a quantity depending on the genus of x. And here the quantity d Aracale of x is just nothing but the normalized regularized determinant of the Laplacian associated to the Aracale metric. So I had the Aracale metric defined as residual canonical metric, and then you take the Laplacian to this metric, and you have the regularized determinant as we have seen in Anna's talk, and you normalize this by dividing by the Aracale volume of x, so to say. And I don't write it down, but the number Ag of x, this is explicit linear function in the genus of x with the usual suspects like log pi, log 2, and the derivative of Riemann zeta at -1. So you can explicitly write it down. For us, it's just to be kept in mind. It's linear in G, in the genus. Okay, and basically that was the starting point to translate, so to say, this definition, which was a translation of Faltings' original definitions of his delta function, to translate this into hyperbolic terms. And so I can now give the theorem, and then you see it's a little ugly, but I mean that's the first thing, and you get what you get. So probably, yeah, well, I'll leave Selbach zeta for a moment because it shows up again. So it's the theorem. So x as above, compact Riemann surface of genus bigger than 1. And then let f of z be defined as this strange integral from 0 to infinity. You integrate this heat kernel on the diagonal where the identity term has been omitted. Make it convergent by dividing, by subtracting the constant term, so to say. So now it's convergent, and then you can integrate along t, so you get a function of z. And then we have the following formula that the Faltings delta function turns out to be 2 pi times 1 minus 1 over the genus of x times the integral over the surface, this function f of z, Laplacian, hyperbolic Laplacian applied to the function f of z, and then integrated with regard to the hyperbolic volume element. So that's the first summand, and then there are 2 other summands. So I just continue here. Minus 6 times log the derivative of Selbach zeta at 1, plus 2 times this limit I mentioned, the log derivative of the Selbach zeta at 1, I mean the constant term. And then plus a plus a function, a linear function again of x, so where again c of x, cg of x, explicit linear function in the genus of x, again with log pi's, log 2's, and derivatives of Riemann zeta function at -1. And you see now this is, I mean, at least it fulfills the promise I gave that you have an expression which is completely in hyperbolic terms. So that's a hyperbolic object, and then you make this integral. You have the Selbach zeta function, its derivative, and here the log derivative showing up. So that's the expression you get, so to say. And then the task was, I mean, to work from that to get estimates which we have not been able to derive from the immediate definition given by Faltings using theta functions. Okay, but probably before I continue and go to estimates, maybe probably what time? Yeah, this, yeah. So idea of proof, so to say. So basically it's 3 steps. So the first step is Polyakov's formula. Which allows you to go from Arakelov metric to hyperbolic metric, so to say. And in terms of this quantity dr, which I had above, there's a formula which tells you that the 2 regularized determinants for the Arakelov metric, which I have written there, and then you can do the same object replacing Arakelov by hyperbolic. These are the same up to some correction term, which is of this form. And here you have the conformal factor. That's the conformal factor describing the change from Arakelov metric to hyperbolic metric. And then here you have the canonical metric of z plus the hyperbolic metric of z, where you integrate against, so to say. So that's the first step to establish this formula. So that's almost immediately done. Then you have a Sarnak's formula for this gadget, which tells you that the d hype of x is the log of Selbach zeta derivative at 1 divided by the hyperbolic volume of x, plus, again, some linear function explicit in g of x. And then the last ingredient, probably it fits here, so if I write not too big, it fits here. The last bit is basically, well, now you have to take care of that, to take care of the translate, so to say, this pullback from the flat metric, from the Jacobian into hyperbolic terms. And then also, once you have done this, once you understand this, this will also help you to understand the conformal factor phi Arakelov. And that's basically this relation which has been established that the canonical metric is expressed by the scaled hyperbolic metric. So here I scale, I divide the hyperbolic metric by the total volume, plus 1 over the genus of x, plus something, if you want, cohomologically, which is a boundary, so to say, which has to be, right? It's the dd bar, so to say, so it's the Laplacian applied to the heat kernel on the diagonal dt, and it has to be a form, mu hype of x, mu hype of z. So you see this, the right-hand side is purely hyperbolic, and this translates the canonical metric here in hyperbolic terms, and you then can also use this formula to give a hyperbolic expression for the conformal factor, which comes here, and once you do the bookkeeping properly, then you end up with that formula. Okay, so yeah, so once this has been done, then we turn to a first estimate, and then you see that the situation simplifies somewhat, but not satisfactorily. So then one has to continue, so to say, estimating. So I need just 4 additional pieces of notations. And the point is they already, I mean, at first sight, at least some of it already looks a little bit ad hoc. But this has to do with the estimates I'm giving here are not by no means optimal. Basically, it's just, it was the challenge to prove that it's possible, so to say. Of course, one can fine-tune things. People who like to fine-tune things can do this, I think. They like that. Okay, so the first thing is lambda x is 1/2 of the minimum between the first non-zero eigenvalue and 7/64. So you see this is somewhat ad hoc, that 7/64 turned out to be useful. Then this is not ad hoc, so this is a quantity which has been studied by many people. The number of small eigenvalues, so to say. So the lambda xj is between 0 and a fourth. The next thing, is for me less known to be studied. So the number of small geodesics, and here it's between 0 and 5, and this 5 again is ad hoc, so to say. It's not really conceptual. So it's the gammas in this primitive conjugacy classes of length between 0 and 5. And last not least, this quantity, the S sub x. So this is a supremum quantity. So this has been studied by various people. So it's the ratio between the canonical metric and the hyperbolic metric, or the scaled hyperbolic metric, in fact. Okay, so these additional pieces I need, and then when you do the analysis, I mean, this is quite a bit of work, not really enlightening, but still, if you do the dirty work, then you can end up with a corollary which gives a bound on Faltings delta function in various quantities. I mean, the ones which we aim at from the very beginning, but then various others still. So corollary, basically working from that formula, more or less straightforwardly. So with the above notations, get the following bound. Faltings delta function can be bounded from above by a constant, which is effective. So it's the genus of x plus 1 over this quantity lambda x, which is roughly speaking the first non-zero eigenvalue. I mean, it's slightly corrected there, times. Okay, then it's the genus of x times the supremum quantity plus 1 squared plus the Huber constant, which comes from the prime geodesic theorem, plus the small eigenvalues between 0 and a fourth. And then the parenthesis is closed, so this 1 over lambda x takes care of these three quantities. And then comes the, so to say, geometric contribution 1 over Lx. So Lx I have not defined, I just realized. So Lx is just Lx, length of shortest closed geodesic on x, times the number of small elements in curly H gamma. So then the big parenthesis is closed with, well, a rough, you can take for D1 to be 1000 if you want. Can do better, but okay, that will. Okay, so now you see, from a point of view of estimates, this is already quite, this is good. I mean, you won't get around the smallest eigenvalue, but of course this is unpleasant, so to say. This is of course also unpleasant, also this, and also this, so to say. I mean, the length of the shortest geodesic also is going to be there. So the things which are circled, we have to get rid of these things. And that's basically what we have done then in the past. I mean, for these two things in the past couple of years effectively. And let me now just, I won't go into too many details, but just give you the results. And so that's now, so to say, the next section. Okay, so now comes effective bounds. Oops, that's the wrong thing. Okay. Effective bounds. For Faltings delta function. Okay, so the first thing is, let me attack this supremum quantity. So first, bounding Sx effectively, so to say. Okay, so let's recall briefly how was it defined. So it's probably still up there. Yes. So Sx is the sup of all z in x, the ratio of canonical by scaled hyperbolic metric. Okay, so you know that the volume is, the volume is 4 pi times gx minus 1, right? So you can then replace the scaled by the hyperbolic metric, dividing by this volume, which then comes into the numerator, so it's then less than 4 pi times the sup z in x, gx times mu canonical of z, if I omit the minus 1 here, by the hyperbolic metric z. I'll just write it like this. And now this quantity is interestingly detected by another heat kernel, I don't want to torture you too much with heat kernels, but let me just mention the following. So there is, I had the heat kernel, so to say, for weight 0 forms, and you can also look at the heat kernel for weight 1 forms. So I denote it by kh upper 1. Also depending on 2 variables, and it's again a function which depends just on the hyperbolic distance when I do it for the universal cover. And then you have again an explicit formula, which now involves also some Chebyshev polynomial. So, but it's a slight twisting of the formula you give for the heat kernel for functions, and again by averaging, you get the heat kernel, and I just write it on the diagonal, because then the formula is somewhat easier. You average again over the group, and then you have here some root of unity, not a root of unity, but something of absolute value 1. And then you have kh 1 t z gamma z with, well, some automorphic factor. C gamma z has absolute value 1. I don't write it down explicitly. But the point is, this function has a limit as t goes to infinity. This exactly reaches this mu can over mu hype of z when t goes to infinity. So, and it's a decreasing function in t which hits this quantity, so to say. So in order to bound this Sx, S of x, of course, you then can bound this quantity in order that you then can take the sup, of course. So you bound this quantity, but this is bounded if you take any t, so to say, and then you can bound it by this, and then you have to put your hands on this quantity, right? And so that's what we did. I mean, first you try to bound the kh, and then you try to bound the average over all the sum over all gammas, and that just give you the result. And here is, again, as I indicated, there's one choice. I mean, there's lots of freedom being given, and by no means we have optimized this. The point is, as I said, this is a decrease. This is strictly decreasing and reaches as a limit this quantity we are interested in, and then we just took t equals 10, bounded by for time 10. So this just used to be simplifying some formula, so to say, but there was no conceptual reason. So what came out is the following proposition. So with the of notation, we get the bound Sx is bounded by a constant d2 times e to Lx, so the length of the shortest closed geodesic on x, divided by 1 minus e to the minus Lx over 4 to the 5 over 2, with d2 can be taken 1200. So yes, 1200. Okay, so that's as effective as you can do. Okay, so this was the first thing. Now the next bit is the Huber constant. So that's a little ugly, so to say. I mean, we did this a long time ago. We investigated the behavior of the Huber constant in coverings, but we didn't really pin it down individually. But then, with the help of Friedman, George Friedman, we were able also to pin this down effectively. And this is, I mean, by no means a good estimate, but you can do it. So that's now bounding. That's the second piece, bounding the Huber constant. Okay, so I'll just write the proposition. So with the above notation, we have the Huber constant for x can be bounded by a further constant d3 times the genus times e to the 8 pi genus of x divided by the length of the shortest geodesics plus in the exponent. Here is the Lx in the numerator divided by 2. And here also some spectral data come in. So it's 1 minus Sx1 times 1 minus e to the minus Lx over 2 squared. And let me just recall, this is the quantity I already had. So Sx1 is 1/2 plus 1/4 minus the smallest eigenvalue. And the d3 can be taken as, well, 10 to the 11. So that goes quite up, and this is very badly done, so to say. I mean, if you do this for SL2Z, I mean, it's not torsion-free and co-compact, but still, I mean, you can play the game. Then a number like 2 comes out. So there's lots of room of improvement, I guess. Good. So now, basically, we have done this. We have done this. I say something to this in a minute. Well, and I say also something to this in a minute, but that's already very classical and well known. So let me probably just underneath that formula write the theorem, so to say, when you collect all the data together. Yeah, let me do this. I probably erase the D1, then you get a little space. Because we keep this formula, so now. Okay, so that's now, so to say, the theorem, which takes into account all the estimates. So, with above notations, we have the following bound. The Faltings delta function of x can be bounded by another effective constant, d4, times the genus of x times e to the 8 pi genus of x divided by the length of the shortest geodesic plus the length of the shortest geodesic. So divided by 1 minus e to the minus length of short geodesic by 4 to the power 5. So that's, so to say, everything sort of somewhat topological and geometric. And here the spectral data is 1 over this lambda x quantity, which has disappeared, and 1 minus this Sx1, which is still on the board, I mean the Sx1, which is here, with the d4, or where d4 can be taken like 10 to the 15. Okay, so this basically fulfills what the original goal was. I mean, we have a bound in terms of the genus, so the topological quantity, then the length of the shortest closed geodesic, and so to say, the shortest eigenvalue, the smallest non-zero eigenvalue, right? So, and now just to complete the proof analysis, I mean, you have the bound from the corollary up there, and we analyzed already the Sx and the Huber constant. So you have the Huber constant there and the Sx there, so you can substitute. So you see there's the spectral information and the length of the shortest closed geodesic coming in. And now it's just to recall the two missing ingredients. So this proof idea. Well, as I said, use corollary above and insert the bounds for Sx and the Huber constant, and for the number of the small eigenvalues of x, which are lying between 0 and the 4th, you have this bound. This is by Peter Buser, so he has this bound that this is less or equal than 4 times genus minus 2. Well, it's 4 times genus, right? So that's Peter Buser. That's an old result. And basically the geometric spectrum, if you want, between 0 and 5 is somewhat played back to the Huber constant using the prime geodesic theorem. Because, I mean, you can say, well, that's nothing than, by our normalization, the prime geodesic counting function pi x of log 5, which then by the prime geodesic theorem you can estimate, and what comes out when you do the calculation, it comes out this, well, it comes out the eigenvalues, again, between 0 and the 4th, plus 3 times the Huber constant. And of course, this we have done up here, and this we have done up there. So this plays back the estimates to the two things we already have. And then you just plug in everything and do the bookkeeping and do the algebra, and then comes out this theorem. Okay, so how much time I have left? A couple of minutes, a few minutes. Okay, so let me make two remarks. So two remarks. So first, if your x is defined over a number field, then you can use the Bieli uniformization to describe the complex points of x, and then you know that the group which uniform